All right, Shreyas, can you see my slides?
Yep.
All right, let's get started. Tonight is a fun lecture. We'll be talking about applications of machine learning. As part of this lecture, we'll discuss a general framework for how you might go about building a machine learning project or a machine learning based product. We'll take a look at an example of a simplified version of this based on a certain Kaggle competition problem. And we'll use all of the concepts we discussed so far in this course. And actually maybe one or two concepts that we haven't talked about that might be interesting for you to go about and learn on your own later on. And then we'll look at two real-world problems which the Community AI founders, Shreyas and Shraman, have created. Both of those are award-winning projects, so should be a pretty exciting night. So on the next slide, I'm going to show a kind of simple framework for implementing a machine learning project. It might look a little complicated, but we'll go through it. For a small project, such a well-defined framework might not be necessary, but it's a good idea to generally keep the major steps in mind. And if you're interested in reading a little bit more about this, I actually took this project workflow from a article on towardsdatascience.com. So feel free to look this up after the lecture. So in this chart, the project is broken up into 4 phases. Those phases are scoping, research, development, and deployment. And there's 3 different types of activities. There's product definitions and product design, data science, and data engineering. So we start at the far left in this scoping phase. And here's where we really think about, what are we trying to build? What's the purpose of this project? What's the product need? And from there, we move on to this initial solution ideation. Basically, we think, what are some different ways that we could go about solving this problem? For example, if we're trying to predict a numerical value, we might think about, well, we know some regression algorithms that we could use. Do we think we've got data, or could we collect data? And that's kind of the next step, is preparing the data and making sure we have access to it. So that might be partially in part of the scoping phase, because we can't really go any further than this if we don't have data available. But it might extend a little bit into the research phase as well if we need to collect some of the data. And then we also need to talk about the project scope and the KPIs. So KPI stands for Key Performance Indicator, and it's essentially how we go about measuring success. So for example, we might say our model's successful if it has a mean squared error less than a certain number, or we predict a certain, all of the classes with 95% accuracy. This really depends on the specific project and who you're doing the project for. Then we move into this data exploration phase, where we get to know our data. We can't just go about machine learning until we've taken a look at the data and figured out, what does it include? What is there anything missing? Do we need to collect more data? And we just need to understand general relationships between the variables we're looking at. And then this next step is pretty important, and sometimes people tend to skip this step, but it's a literature and existing solutions review. So if somebody's done a project similar to the one you're working on, you should take advantage of that. You should learn from the mistakes that they made and learn from the tricks that they've uncovered. There's no reason to start from scratch. You can, this is a very collaborative field, and I'm not suggesting you go about stealing someone else's model, but you can learn from them and find the best tips and tricks for going forward. And then before you really go into the heavy development phase, you want to do a technical validity check. Basically here, you want to make sure that you think the project's going to be successful. Because if it's not, especially in business, you don't necessarily want to waste your time and money developing something if you don't think there's a high probability that it's going to be successful. Next, we've got to build a development and experiment framework. We'll talk a little bit about that on the next slide. And then the major step is the model development. So this is kind of what we've talked a lot about in this class so far, is the different types of models we can build. If it's classification, we might choose support vector machine or logistic regression or a neural network. If it's regression, we might again choose a neural network or linear regression. We've got lots of options here, and there's a lot of model types that we have not had a chance to discuss because this is such a short course. And then we test this model just to make sure that it's working as we want. And once it's working as we want, we'll go on to the productization and monitoring phase, basically delivering that solution and making it something that others can use. So again, just to reiterate, what are the basic steps? Well, first we need to define what we want to do. What do we want to achieve? That's the product definition. There's the initial solution ideation phase. What are some ways we can solve our problem? We want to define the scope and the KPIs. So the scope is essentially what problems are we tackling with this project and what problems are not part of this project. So this is important in business because projects have a tendency to grow bigger than they were initially intended because people get excited and want more and more features. But sometimes it's best to just put a boundary upon what you want to do with the initial project and maybe tackle those extra features later on. And then the key performance indicators we talked a little bit about, but this is essentially how we're going to measure whether or not we're successful. And you should, if you're doing this for business, always agree upon the scope and KPIs before you really get started. That probably doesn't matter a whole lot for us since we're looking at kind of defining our own projects that help the community, but we should really focus on scope and KPIs in terms of how successful we are with our project. Then the data preparation, accessibility, and exploration phase. We need to get access to the data. We need to make sure it's in a good format, and we need to get to know it, understand the nature of the variables and the relationships between variables. Perform a literature review. Basically, has anybody solved this problem before? And then we want to build a framework for model development. So this involves writing reusable functions or routines that can help with things like calculating the key KPIs, preparing the data, and training various models, because it's always we're likely going to train more than one model, and we don't want to have to rebuild everything from scratch each time. Then the bulk of the work, again, that I mentioned, is in this model development phase. We're going to identify model options, build the models, train the models, and score the models. And it's an important point here that this is an iterative process. You might train a model, learn about one of its deficiencies, and then have to find a way to improve it. So we'll actually kind of take a look at that part in the code demo in a few minutes. And then we need to implement the final model. You might need to write a program to make your model usable by others. You might need to make your model available to external software. But if you're doing a small project, we might just kind of skip this step. It might be integrated with step 7 above. And then we need to deploy this solution, make the product available to others, and make sure others know how to use our product. So with that, we'll just go into a demo. This is a Kaggle competition about predicting home prices. So you could think that something like this might be important for a company like Zillow or Realtor.com or one of the other many real estate sites or apps in which they want to provide users not only what the seller is asking in terms of price, but what they think a good price is. So we'll dig into this data here. All right, Shreyas or Shaman, can you see my code now?
Yes.
Excellent. So as always, I'm going to get started by importing some functions and libraries that we're going to need. And at the top here, you'll be able to look at this code after the lecture, but there's a link to where I got the data from. And the data set is a collection of property sales in a single city in Ames, Iowa. And for each property that's sold, I've got a typo here, so I'm going to go ahead and fix that on the fly. There are a variety of features that are captured, and we'll go ahead and look at those. So I'm going to import pandas. That's something we've done many times so far in this class. We'll import matplotlib, so that's for creating plots. And then from the sklearn linear model package, I'm actually going to import two functions this time, or two routines. One is the linear regression. We've seen that before. And the other is called a ridge regression. And ridge is essentially a regularized version of linear regression. So that's something that we talked about in lecture 7, how to make sure we don't overfit. Ridge is an example of a model that has the capability to tune that regularization parameter and make sure our data, our model isn't overfitting. You've seen this before, this train test split function from sklearn, basically creating our training and testing data sets. And then a couple of things that we probably haven't talked a whole lot about. There's this function called PCA, or Principal Component Analysis. It's not something you're expected to know about, but it's another way to prevent overfitting by doing a little bit of pre-processing and pulling out the components of your data that are really most important or most pronounced. I'll also build a neural network using sklearn's MLP regressor. And finally, one other type of regressor that we haven't talked about called gradient boosting, or gradient boosted trees. And then finally, NumPy. So we've seen NumPy before. So I'm going to load this training set. And there's one column that I'm going to drop because it's actually not predictive. It's just an ID number for each of the houses. So I'm going to load the data. All right. And I'm going to take a look at this data frame. All right. You can see there are a lot of features. I'm not going to talk about all of these, but we'll go through an example of what some of them are. So there's a MS subclass, which tells us what type of property it is. There's MS zoning, which tells us how the property is zoned. This RL stands for residential low density. You can see RM, there's residential medium density, and later on you'll also find things like RH, residential high density. And we can see how big the lot is, whether it's on a paved or gravel street, the shape of the lot, what utilities it has. So for example, does it have access to electricity, natural gas, water, and wastewater? We've got some different neighborhoods that these homes can belong to, the condition of the home, the style of the home, and then some features about the quality and the condition of the house, the year it was built, and maybe the last year it was remodeled. What is the outside of the building made out of? What condition is that in? And so on. So we've got whether or not there's a basement, how big the basement is, how many square feet are on the first floor, how many are on the second floor, and so on. And some of these variables might actually be missing. So that's actually one of the first things we're going to tackle. So I'm going to go ahead and go back to the code. All right, so when I was doing, I'll turn this to true. When I was looking at this data at the beginning, I wanted to see, for example, what was the breakdown in how the houses were zoned and what subclasses they belonged to. So popping up a few images real quick. For some reason it's taking a few seconds here. It shouldn't take quite that long. I'm going to go ahead and stop it and try it one more time. Well, it doesn't appear to want to plot tonight. So essentially, I wanted to take a look at what fraction of the homes were in each type of zoning category and subclass category, just to get an idea about what's in this data set. And as part of that, I noticed that there were only a very few number of properties which were zoned commercial. And for that reason, I decided let's only focus on the ones that are zoned residential, because residential and commercial properties might be very different. So I'm going to drop the commercial properties. All right, that ran quickly. And then I'm going to take a look and say, how many elements are missing from each field? And I've actually computed the results already and put them here in a comment, but I'll go ahead and run that quickly. And so what you can see is a lot of the variables are missing data. 259 out of the 1,450 are missing the lot frontage variable. Almost all of them are missing this alley variable. And then we can see some more, like the one at the bottom here, this pool QC, 1,443 out of 1,450 don't have a pool, so they don't have any comments regarding the quality of the pool. That kind of makes sense. So this isn't really an issue. But let's investigate a couple of these features independently. So let's look at this miscellaneous feature at the end. All right. So if I look at the data dictionary that was provided, which essentially tells us a little bit about each data point, it says that miscellaneous features, this category is used to describe miscellaneous features that are not covered in other categories. So maybe there's an elevator in the house, or a second garage, or a shed, or a tennis court, or maybe there's none. So it turns out that none is actually an acceptable value, and it doesn't actually mean that we're kind of missing data. It really just means that the miscellaneous feature is none for that. So we can go ahead and replace those with not applicable. So that's what I've done here. I've said for all the variables in the miscellaneous feature column that are empty, we're going to fill those with not applicable. And I'm just going to do that in place. So I actually already ran that, but I'll run it again. There's a lot of other fields in which NA is actually acceptable too, based on reading the data dictionary. So for example, if they don't have a pool, well, there shouldn't be any comments about the pool. If they don't have a fence, there shouldn't be any comments about the fence. And that same thing is true if there's no garage, or if there's no fireplace, or if there's no basement, or no alley. If none of those things exist, we shouldn't expect there to be data for them. So we'll just replace those NaN fields with not applicable. And this will allow us to do our one-hot encoding later on. All right, so after we do this, we can see which values are still missing. And it turns out there's 5 of them. There's lot frontage. So basically, how many feet along the property are connected to the street or are visible to the street? What type of material was used on the front of the home? A description of how the quality of the electrical componentry in the house, and the year in which the garage was built. So if we look at the year in which the garage was built, we can see that there's 79 missing values. But if we scroll back up, we notice that there were also 79 missing values for all the ones with garage type, garage finish, etc. So I think that's just another one of those from above where the home didn't have a garage. So we'll go ahead and just replace the year that the garage was built with the year that the home was built. And you might be wondering, why am I doing this one differently? Well, it's because for this field, I can't really put not applicable because it's a numerical field, where all the other fields were categorical. And so here, I'm just going to replace the year that the garage was built, which was empty, with the year that the home was built. And this isn't necessarily 100% accurate, but it probably doesn't matter because we already have another field that tells us whether or not there's a garage. So it's probably not that important when predicting the value of the home, what year the garage was actually built. So there might be a better way to do this, and that's something that I challenge you to go think about on your own. Is there anything else that we could have replaced this with? I wouldn't want to replace it with the value 0, because that's not going to be on the same scale as the rest of the values, because most of these homes were built in 1940 or 1950 or later, so 0 would appear to be an outlier and could affect our model. We'll look at the missing value for electrical next. And if we look at the record, it was a recently built home. And the home, it says it was in average condition. So I'm just going to assume that it has a standard circuit breaker. That's one of the different categories according to the data dictionary. And since it's only a single record, even if I'm wrong, it probably doesn't matter too much. But again, feel free to think about this one on your own and come up with a potentially better way to fill in this missing data piece. So I'll go ahead and run that. All right, so now we've only got a couple of data fields left that have missing data. We'll look at the masonry veneer type, masonry veneer area. These 8 records that are missing each of the same 2 values. So we'll deal with each of these records simultaneously. And in general, if we look at all the other homes in the data set, well more than half, probably about 60 to 65%, don't have any masonry on the front of the home. So I think that's probably the best thing to replace these missing values with, and just assume that if they had had either brick or stone on the front of the home, that it would have been captured in the data set. Again, this is probably wrong. Well, I don't know, maybe it's right. I have no way of knowing. Maybe you can come up with a better way to fill in these missing values, but I'm going to say that the type is none and the veneer area is 0. Again, I'm working towards creating a complete data set which has no missing values. The other option, of course, would have been to just drop all of these observations that had missing values, but I think it's more interesting to try to fill them in. That's something that you'll have to decide upon on your own when you're looking at your project. Which is better? It's hard to say. There may not be a definitive answer, but you can try different things. The final feature that has a lot of missing variables is the variable lot frontage. So as a reminder, this is the number of feet of the property that are exposed to a public street. And that could impact the value of a home. So we want to try to be smart about this, right? You might not want a home if it's buried behind other homes and doesn't actually have much access to a street. So we'll do something that's not super sophisticated, but still makes sense. And the first home with a missing lot frontage is the observation at index 7. So if you want to take a look at that, I'll go ahead and do that real quick. Index 7 here, we see it's missing lot frontage, but almost all of the other variables are still filled in. So let's see if we can try to predict lot frontage based on some other variables. And again, this isn't going to be right. We're not going to get it exact, but it might, it should work well enough for this application. So let's build a model using homes with a similar type to predict the lot frontage. So I'm going to say that two homes are similar if they have the same MS subclass, that's the type of dwelling, if they have the same lot shape, and they have the same lot configuration. So if they have the same lot shape and lot configuration, it probably means they have generally the same type of access to a road. And we'll try to predict the lot frontage as a linear function of lot area. So for each one of the records in which the home was missing the lot frontage variable, I'll pull out the subclass, I'll pull out the shape of the lot and the configuration of the lot, and I'll also pull out the area of the lot. And then I'm going to find all of the other homes in the data set that have the same subclass, same lot shape, and same configuration. And I'm going to look at their lot area and lot frontage. And just in case one of the other missing data points is also in this set, I'm going to go ahead and drop those. So if there's not enough data in that subset, I might go ahead and relax our restrictions. So say that maybe it only needs the same subclass and same lot shape, or if there's still not enough records, I'll say that there's only the same subclass. I'm going through a lot right now, so if you don't follow everything, that's okay. You can take a look at the code later. But now I'm going to build a model that predicts the lot frontage from the lot area. So I do that by creating a linear regression model and fitting it based on all of the other homes in the data set that are of the same type, remember, and I'm going to predict their lot frontage based on their lot area. And then for the data point that was missing, remember I took a look at its area earlier, I'm going to use that lot area to predict the lot frontage, and I'm going to replace it in the data set. So that was a lot. And essentially what you can see is I'm using machine learning to fill in my data set so that I can apply a machine learning algorithm later on, which is kind of a cool idea. And again, there's probably a lot of different ways to go ahead and fill this in, but I just wanted to show you something that I thought was interesting. Next step in the data pre-processing kind of arena is replacing categorical variables with numerical variables. We talked about that a little bit in the previous lecture around categorical encoding or one-hot encoding. So you'll see there's a lot of features here that are categorical. I think there are about 44 or 45. Luckily, Pandas has a nice function called get dummies, which will allow us to encode all of these features at the same time. So I'll go ahead and do that next. All right. And now all of our data is represented with numerical features. And we've gone from a data set that originally had about 80 features to now we have a data set that has 282 features, because each one of these categorical features now has a number of columns associated with it based on the number of different categories in that feature. That was a mouthful. All right, but now we can apply normalization. So we'll divide by each feature's mean, or sorry, subtract each feature's mean and divide by the standard deviation. And we'll also pull out the sales price from the data set, because that's what we're trying to predict. Now here's something we haven't talked about really at all. I mentioned this in the beginning of the code demo, but I'm going to perform principal component analysis, which is going to take those 281 features and I'm going to reduce it to about 90 features. So essentially, this is going to throw out those features or a kind of a rotation of those features, you might say, and throw out all the ones that we don't think are too important. Again, I recommend that you go and read about this on your own if you think you're interested. Uh-oh, input contains a nan. I must have forgotten to run one of these. So I'm going to start from the top and make sure I ran all of my fields. Oops. I'll go ahead, run that. Oh, skip the plotting. Right, and then hopefully the PCA works. All right, now it works. So I must have just forgotten to run one of my cells. And then, as we've talked about a few times, I'm going to use the train test split function to take my X and Y variables and split them into a training and testing set. And here I set a random state, and that's just so that it'll give me the same X train and X test every time I run this. But in general, you may want to not freeze your random state so that you actually get a different random set every time you run it. And the first thing I'll do is try linear regression. That's always a good starting point. So I'm going to fit the model, and then I'm going to compute the R2 score, and I'm going to compute the mean squared error. I'm going to do that for both the training and the test set. All right. So first, and I should point out that I've done this on the data after I applied principal component analysis. So this is linear regression with PCA. The R squared value on the training set is 0.83. The R squared value on the test set is 0.85. So this is one of those rare occasions where we actually perform better on the testing set than we did on the training set. And you can see that the mean squared errors, they're about the same order of magnitude. So we built a pretty good model. It doesn't appear that we're overfitting. So since we aren't overfitting, you might say, well, maybe we should have tried to just run linear regression on the entire data set with all 282 features. So I'm going to do that. I'm going to run this model now without using PCA. So let's see what happens. Okay. Well, this isn't good. I'm plotting the PCA predictions against the predictions using the original data set, and we see that using the original data set with all 282 features gave us some home price values that were just crazy. We've got some that are negative and very large, 1.5 times 10 to the 16th. That's pretty expensive property in terms of dollars, so that can't be right. Let's go back to the code. And what we can see is the R squared value on the training set is actually much higher than it was before. Before it was 0.83 when we had applied PCA. Now it's 0.94. But look, we've got a negative R squared value. That's something that should never happen. And the mean squared error is super large. So why did that happen? Well, essentially it means that we've overfit so badly that we would have just been better off predicting the average price of all the homes in our training data set for the testing data set. So this model is actually worse than if we had just, picked something silly like the mean or the median. And the mean squared error is huge, so that's no good. So let's go back to the data set with Oh, never mind. We'll do something else. Let's try to apply regularization instead of using PCA. So we can use the original data set with all 282 features, but apply a pretty big regularization term. So alpha equals 1,000. That's equivalent to the lambda from the lecture from last week. So I'll go ahead and run this model. All right, now the PCA predictions and the ridge regression predictions are roughly the same. So you see this nice linear relationship. That means they're generally creating the roughly the same predictions between the two models. And here we've seen it's much better. The R squared on the training set is 0.87 and the R squared on the testing set is 0.87. That's perfect. Essentially, we haven't done any overfitting because they've got the same accuracy. So that's good. We've got an R squared of 0.87. I like that. Our mean squared error is decreasing a little bit, but I'm kind of curious if we can do any better. So we could try a neural network. So I've played around and found a neural network here that works fairly well. I'm applying a little bit of regularization to that neural network. And you can see here are the size of each of my hidden layers. I've got a layer with 128 nodes, and then 2 layers with 64 nodes, 2 layers with 32 nodes, and 2 layers with 16 nodes. So I'll go ahead and do the same thing, compute the R squared value and the mean squared error. And this takes a little bit longer, but not too bad. Here we see that the R squared value on the training set is really high. It's actually 0.95. So that seems good, but we see that the R squared value on the testing set is 0.85. So that means we've probably overfit quite a bit, and maybe we need to kind of remove one of our layers or increase the regularization term. I'll leave that for you students to maybe try on your own. And then there's one other type of model that we haven't talked about, but is actually quite powerful. And so I'll recommend that you learn about decision trees and random forests, and then later on gradient boosted trees on your own. But it turns out that sklearn has an implementation of this called gradient boosting regressor. So I'm going to try that. So it's going to build 1,000 different decision trees, and it's going to take the average of all of those different decision trees to try to compute a sales price. And what we'll see when I do this, takes a few seconds because I'm building essentially 1,000 different models. I'm going to combine them all at the end. But the R square valued on our training set here is 1. That means we've predicted the sale price almost perfectly for every house. It's not exactly perfect. It's just rounded to 1. It was probably 0.995 or 0.996, something like that. But it's actually a much lower mean squared error than we've seen before. And look at this. We've actually gotten an R squared value on the testing set of 0.92. Well, this tells me a couple things. First of all, this is the best model we've seen. That's the highest R squared value for all of the models we've trained so far, and the lowest mean squared error, which is great. But we might still be overfitting a little bit since the R squared value is higher on the training set than it is on the testing set. So again, we can maybe play with these parameters to make sure that we're not overfitting. But this is still a very good model. So just to wrap up, sorry, Shreyas and Shraman, that I've taken so long, but we loaded the data, we filled in the missing values, we applied some normalization and a little bit of feature pre-processing, and then we trained about 5 or 6 different models, and until we finally found one that seems to be the best performing one. So this is a lot of what a machine learning project might look like. Generally, you're going to spend more than 20 minutes figuring it all out, but there's a lot of different models you can play with, and each one of those models has a lot of different parameters. So it's important to kind of keep in mind what you're trying to do and keep in mind those concepts of overfitting and underfitting to try to build the best model you can for your application. So I'm sorry I've been talking quickly. I encourage you to go back and rewatch this video after we post it and look at the code and read it in depth, and so you get a better idea of what's going on. But with that, I'll go back to the slides. Actually, Shreyas, do you want to just take over?
Yep. Thank you, Dr. Willard. Yep. Yeah, I can take over, yeah. Let me share my screen. All right. Can everyone see my screen okay?
I can see it.
All right, thank you. All right, so thank you, Dr. Willard, for the great lecture. So now I'll actually talk about one of my personal projects that I worked on regarding machine learning. So I'll be using the same sort of framework that Dr. Willard introduced in the lecture today. So let me first define what my project actually was. So I developed an early diagnosis tool for the detection of Parkinson's disease. So first, let me actually define what Parkinson's disease actually is. So Parkinson's disease is a disorder of the nervous system, which is characterized by uncontrollable tremors or shaking. And Parkinson's disease is actually a very prevalent disorder. And in fact, over 10 million people suffer from Parkinson's disease all over the world. So this problem is a very impactful problem. And now let's talk about why early diagnosis of Parkinson's disease is so important. Why can't regular diagnosis, why isn't a regular diagnosis okay? So this is the reason why. So in order to actually show this, let's actually talk about how exactly Parkinson's disease occurs. So Parkinson's disease occurs due to a shortage of a specific neuron called dopamine. And dopamine is essentially a neuron which helps in communication or signaling to other nerve cells. So it essentially sends signals to other nerve cells. And PD patients often have, or PD, by the way, is a short form of Parkinson's disease. So Parkinson's disease patients have a low amount of dopamine. They have reduced amounts of dopamine when they get the disease. However, it turns out that when PD patients are diagnosed currently, well, what happens is that a lot of dopamine is already decreased. So treatments and many things similar to that are less effective, as if they had dopamine, as if they had a lot of dopamine already when they were diagnosed. So to combat this problem, an early diagnosis system could potentially save a lot of dopamine and thus greatly increase the quality of life of PD patients. So that's why an early diagnostic system is so important. And now let's move on to the next step, which is the initial solution ideation. So what was my initial solution? So I knew that I wanted to use a machine learning algorithm to actually diagnose Parkinson's, early. However, my next step, which gave me a lot of trouble, was what features in particular could I use for diagnosis? So for that, I looked at sort of the symptoms that most Parkinson's patients face. And these are some of the common ones. So there's tremor, slowed movement, rigid muscles, speech changes, writing changes, so on and so forth. And I decided on using voice-based features for one big reason. That is that changes in difficulty in speech is one of the first symptoms that a Parkinson's patient exhibits. So that's why it would naturally seem good to use voice-based features to actually diagnose this disorder early. And initially, I knew I was going to use some sort of classification model, but I wasn't too sure on what I was going to use initially. So initially, I thought I was going to use a neural net, and I did at the end. But here I was sort of fuzzy on the exact details on what I was going to use. So I tried a lot of different models. So now let's move on to sort of the scope and which testing metric I used. So before I actually do that, let's actually define our problem just a problem a little more analytically. So essentially what the problem was is for a standard voice sample, calculate various voice-based features, and that would serve as the actual input to the model. And the output of my model was going to be some binary value between 0 and 1. And 0 was just when the patient didn't have Parkinson's or wasn't predicted to have Parkinson's, and 1 is when the patient did have Parkinson's. And as I said before, my data set consisted of a ton of voice samples, and ton of voice samples. And however, as you learned in the last video, in the last lecture actually, it isn't very advantageous to use all of your data for training and use the same data for testing. Indeed, a lot of times you would want to, sort of separate your set into training set and testing set, as you can see here. And so I left approximately 30% of voice samples as testing, and I gave the rest 70% for training the actual model. And in terms of my KPI, I use F2 scores as the testing metric, and I'll talk about what F2 scores is in just a second. And my testing metric was if the F2 score was greater than 0.87, then it was successful. And I got to that F2 score after reading a lot of literature in the field of diagnosis with Parkinson's disease. However, let's look at this equation. So now let's actually talk about F2 scores. So Dr. Willard, in his logistic regression lecture, already introduced the idea of a F1 score, okay, of F1 score. However, in a medical scenario, when you want to prioritize minimizing false negative cases as opposed to false positive cases, then an F2 score model is advantageous. And this is the equation for F score. And if you plug in beta equals 2, you get the equation for a F score. Okay, so that's what I used as my testing metric. Now let's move on. Let's now introduce sort of data preparation, accessibility, and exploration. So as I said before in this slide, I was going to use voice-based features as inputs to my study, to my model actually. So now let's actually determine which voice-based features to use in particular. And to actually do that, I again performed extensive literature review to determine which features to use in particular. And this is a very common trend in data science. Literature review actually takes quite a bit of time and is really, in some projects, at least in this project, is very useful. Is very useful to actually develop the model. And after extensive literature review, I determined that these two features in particular were the best to use. So pitch period entropy and spread one. And I won't go into detail on how exactly they're computed or what they represent. Okay, so let's move on. So now let's go to literature review. So here I hinted on how important literature review was, but let's talk about this in greater detail. So currently there's been very little research done on using machine learning for early diagnosis of Parkinson's disease. So some of you maybe, and this is actually interesting just because you hear a lot of hype on early diagnosis, but in fact, this is a field that has only been around for the last few years. So there aren't many papers regarding early diagnosis of Parkinson's. However, I could find a lot of papers focusing on sort of the standard diagnosis of Parkinson's using machine learning. And those are the papers I had to read to actually determine my features and things like that. So now let's actually move on to sort of the model development part. And before we actually move on to model development, let's think about how we can build a framework for this model development. So before I actually started developing, my classification models, I had to first write code to actually calculate features that I determined that I would use using Octave. So I had to calculate various features such as PPE and spread one before I actually started developing this model. So let's move on to model development. So in regards to model development, I build a classification model using these three models: logistic regression model, an artificial neural network, and a support vector machine. And in this course, we did talk about logistic regression and neural networks, artificial neural networks, but we haven't talked about support vector machines. So if you would like, please do research on this on your own, because this is a really powerful model and a very powerful classification model. And for now, just think of support vector machines as just a model, which is pretty much think of it just as another classification model. The details could remain as a black box for now. And in this step of model development, as Dr. Willard mentioned, this is a very iterative process. And to that end, it's very important to check for overfitting, underfitting, and just small bugs in general, which might interfere with your model. So now we are done with model development, and let's move on to our last step, that is deploying our actual solution. So now, after you're done actually developing the model, what you want to do is talk to stakeholders. So essentially, who you're building the project for, to ask for feedback, to ask for feedback on how you could sort of improve your project. So this is a very, very important step. And if you're especially if you're a middle or high school student, you could present your project in research competitions or conferences and get additional feedback on your work. So that's about it for my project, and I hope you enjoyed it. And I'll be open to any questions after Shraman finishes his presentation. So Shraman is going to now talk about his project, which is actually a very, very interesting project. So Shraman, would you like to start discussing?
Thank you, Shreyas. Could you stop the screen? Thank you, Shreyas. So let me share my screen. So today I want to talk to you about a really project that I'm really proud of and I've worked a lot on. So I created a machine learning algorithm to detect icebergs from satellite images to help reduce global warming, oil spills, and improve safety of Arctic navigation. So let's talk about my initial solution. So my initial solution ideation. So how I went about it. So first, I had to research the best machine learning model to use to do this. And there were two that I really liked, support vector machines and convolutional neural networks, and I tried both of them, but I was only successful. My support vector machine model didn't do as well as my convolutional neural network, so that's what I really focused on. And then I had to determine the best programming language to use, and I was thinking about Octave or Python, but I chose Python at the end. And then I got my data from the Sentinel-1 satellite images, which is actually radar satellite. And then I had to set up the programming language, programming environment, then define my training and testing data. So I used 75% of my data for training and 25% for testing. And then I had to design the CNN model and then run the model for 100 eBotches and then do my prediction of my loss and accuracy. And my success criteria was for my accuracy to be over 85%. So let's talk about data preparation for accessibility and exploration for me. So so my data was the data I received was presented in JSON format, and the files consist of different features like the ID of the feature, band 1, band 2, INC angle, and the IS iceberg. And so the ID was basically the ID of the image, pretty self-explanatory. And the band 1 and band 2 was basically the image data. So the image data was just, each band contained 75 by 75 pixels. And so when a satellite image is taken, in this case, we had the horizontal and vertical pixels. And each of these contained 75 by 75 pixels, and it was all flattened out. So each of these bands contain 5,625 elements. And the INC angle is the incidence angle of which the image was taken from, and the IS iceberg is the target variable. And it's set to 1 if it's an iceberg, and it's set to 0 if it's not an iceberg. And now let me talk to you more about the convolutional neural network, as we haven't talked about it yet in this class. So I'll give you a 3-minute introduction of how it works. So in the convolution layer, the pictures of each picture is converted into an array of pixels, and then a filter is convolved around the image, and then new sets of arrays are created. And then from that, each element is applied to the activation function, and most of the times it's applied to the Rayleigh function. And then from there, we downsize the array. And we usually use, in this case, we have a stride of 2. So for each 2 by 2 array, we take the maximum value and we convert that into a new array. And then we flatten the image out. And after we've done a lot of iterations of convolutional layer and pooling layer, we usually flatten we convert the array into a vector and apply it to a neural network. And that's the fully connected layer. And here's a code snippet. And here are my results. So I had a 90% for my training accuracy and 87% for my testing accuracy. And I actually met my success criteria. And in the real world, a satellite image will be taken and will be constantly, and if any icebergs detected, it'll automatically we automatically notify ships and oil rigs in the area. And now Shreyas will talk about a few details about our next lecture. Oh, Shreyas?
Yep, thank you, Shraman. That was a great presentation. So now let's actually, first let me actually share my screen. Just 1 second. All right, now let's talk about a few details about our next lecture. So next lecture is actually our last lecture, and we'll be talking about many things. So first, we'll start by introducing reinforcement learning. So this is what we were originally intending on doing, but we're going to be focusing on many more things other than that. So this is going to be sort of a session where we can start discussing about our final projects. So secondly, what we're going to do is actually have a group discussion about the final project. You can ask any questions, and we will answer it. And by the way, you can also, if you have a question that can't wait, you can ask on Google Classroom, and we'll answer it. And thirdly, we can also give you feedback on your elevator pitches, on your 30-second elevator pitches. And for now, before we actually give you feedback, you can watch these thesis pitches here. These are actually pitches done by PhD students. Who are presenting their PhD work, in 3 minutes. So this is a very good thing to see, to actually see how you might come about doing one of these. So lastly, we'll be taking a group picture since this is our last meeting. So please keep your camera on for agenda 2 through 4, so we can take the picture. So that's about it for this, and we really hope that you enjoy our next lecture. So now we're open to any questions. Does anyone have any questions? So I see a question in the chat. Could you post a link? Sure, we'll post a link. Okay.
Looks like there's a question for Shraman. What machine learning library did you use?
To create the model, I used Keras. To create the conv model, I used Keras. And I think I already answered that to Douglas.
Oh, sorry. I might have missed that.
If you
Yes,
need help
Keras is a very popular machine learning package for building neural networks. You've probably also heard about TensorFlow and PyTorch, but those are a few of the most common machine learning libraries for building neural networks.
All right, so Severe. So here you don't have to actually do the coding. So this is sort of just the idea generation part. Like the coding isn't mandatory for the final project, even though we encourage you to do it after this camp. See, can the final project be done with a partner? So we don't have any rules on it right now, but yeah, sure, you can do it with a partner if you want to. And would we need to share a? Yeah, I think I answered that. So any more questions?
If anybody's uncomfortable with having their picture taken, you can feel free to leave your camera off. That's not a requirement for the class, but we would like to take one just to, you know, remember how successful this first camp was. I also noticed that there's several folks who have not turned in the homework that's due this evening. So I think there might be a little bit of time left, but if you're interested, please go ahead and do that.
Any more questions? All right. If no one has any more questions, I think that's it for this lecture. So thank you all for attending today. Hope you enjoyed, and see you guys. See you guys in the next lecture. So thank you, Dr. Willard and Strawman. Yeah, see you guys in the next lecture.
Thank you.
Thank you.
Bye-bye.